Hi everyone, and welcome back. So last time we were talking about these cool normal distributions. When I say cool, I'm a professor, so you can take that with a grain of salt. But why is it cool? Well, because this is how error looks in your life. Error is not just, oh, well, one time we got something different. No, error is that in engineering, you never measure something once. Now, you don't normally measure something 1,000 times either, unless it's extremely important. And you have to figure out how many times you want to measure something to get a good idea of what's going on. What we get is that if we measure something 1,000 times, there will be slight amounts of error because we can only be so precise. And precision is how close together my results are. The more precise I am, the less error there will be because I'll be closer and closer to the true average. The less precise I am, the more variation I'll see. So, with that in mind, let's keep on working. So error looks like this too, because if you measure something 100 times, you're going to get 100 different values, and because of that, you get a better idea of what the distribution is. You can tell, well, the true average seems to be here in the middle, and I'm measuring things all around here, but because I've measured enough, I know what the true average is. I also know how precise I am. Now that's great for when you're taking measurements. It's also great for when you're trying to figure out, will my bridge collapse based on how much force is being applied to it? Hopefully not, because that would be pretty terrible. So let's keep going through it. Now right here I've given you 4 different normal distributions just to show you what the difference looks like. They're all sized the same, they're all scaled the same. However, what you see is that if I move the mean, I move the center of that distribution. If I change the standard deviation, if I make it larger, then that distribution gets wider. What that means is that there's just more values all across here. If I make it extremely wide, then it's just like anything could happen because you've got the humongous amount of variation. It's just like more or less a random number generator. So you want things to be precise. That's where all the values are close together. You also want it to be accurate. You want what you're measuring to be close to what's truly there. And that's a different measurement. Precision is the big thing here. Now, I've mentioned the variation, how wide this is, the standard deviation, words like that. Standard deviation is a measure of how spread apart your values are, how wide the values are. And we can calculate it using stdv.p, standarddev.p, and then you select your range of values. There is no if standard deviation, there is no standard deviation A. There is a second one though that does not look like this. I believe it's standarddev.s. Don't use that one, just use the P for this class. There is a difference. What it's saying is that if you have 1,000 values, and you only choose 10 of those, well, you don't want to calculate your standard deviation like this because that's assuming that this is all the data you have. If you have just a small sample, use the other one. We're not going to do that in this class. That's kind of outside the range of this course. But for now, standard deviation.p. Okay, so we're going to calculate the standard deviation of these 4 tools. We measured the force with tool A, tool B, tool C, and tool D. And we want to see which of these tools is the most precise. So the most precise tool would have the smallest standard deviation because it have the less variation in its measurements, or the small variation in its measurements. Okay, so equals stdev.p. I was wrong. There is a standard deviation A and standard deviation PA. Didn't realize they still have that. So you can take into account logicals as well. Okay, so now let's select the range here. Select all this, hit enter, good. Okay, and from this what we see is that tool C has the smallest standard deviation. Switch tool's most precise, and notice there's a little drop down box. I click it, C, and we're good. Now, interestingly enough, I created all these numbers. There's actually a function built into Excel which allows me to choose numbers out of a normal distribution. So I knew what their standard deviation and average was supposed to be from the very beginning. However, I only have about 10 values here. I have, 9 values here. and that's just not enough to get a good distribution. Because I only had 9 values, the standard deviation wasn't actually as close to the true standard deviation as it could be. And so this one, just due to randomness, actually came out winning instead of this one. This was actually supposed to have the lowest standard deviation. But it's the fun thing that happens with numbers sometimes. Okay. Now, let's look at these distributions right here. All of them, all 4 of these sets of numbers, should have the same average and standard deviation. They were taken from the same type of distribution. Now, just because I took them at random from that distribution, doesn't mean that in the end it will look like that distribution because I might have pulled enough. So let's see that. Let's see how it looks. So equals average, and I select all these numbers. That works. I selected way too many numbers because I accidentally typed a 0. Okay. And I'm going to do this one right here. And it's going to say try again every single time because I'm not selecting everything. Ooh, divided by 0. Oh, because this is not nearly the right place. Okay. Cool thing is you can actually take your selection and change its size just by grabbing it. A little pro tip right there. Okay, and this one right here. I want to change the size of that distribution. That one's good. And change the size of this distribution. That one's good. Okay. Now, just looking at the average here, I'm going to let you do the standard deviation on your own because I'm going a little bit long. You see that as I get more and more values, I move closer and closer to the true average, which would have been 25 in this case. So the more data you take, the closer your average gets to the true average. And the closer your standard deviation will get to what the true standard deviation is. So remember this, more data is usually a good thing. Now, more bad data is not a good thing, but more well-taken, consistent data is a good thing. So take as much data as you can so you can get as good a result as you can. Well, I hope this helped you, and we'll do some more with normal distributions next time. I'll see you later. Bye-bye.